The first speaker today is Olivier Debarre, who will talk about birational transformations and periods.
Thank you. Thank you very much for the invitation. So I will start my talk by recalling some facts about cubic fourfolds, which we talked about in previous talks. Maybe I'll start here. Facts. By facts, I mean theorems. So I assume that X is a smooth cubic fourfold in P5, and I'm working over the complex numbers. So the first point, which is easy to show, and it's in Marx's book, is that there is a coarse moduli space for this cubic. So there is a GIT. This is true for all, for hypersurfaces of any degree. Of course, we get this moduli space. For these cubic fourfolds, and it's affine. It's just constructed by the quotients of affine space. The second, this way. The second fact is the Beauville-Delargue construction. So we may consider the space of lines contained in X, so f of X. That was the notation that's usually used. And actually, I want to call my cubic W. Sorry. Because X would be something else. So f of W, the set of lines contained in Y, is a hyperkiller fourfold. And there's an isomorphism of polarized Hodge structures between the primitive homology of W in degree 4 and the primitive homology of F of W in degree 2. So there's a shift of -1. So this is Beauville-Delargue, ED. The third theorem is the Torelli property, which you can state by saying that the period map from W to, from M to some period domain. So this is a quasi-projective variety with a canonical compactification called the Bailey-Borel compactification. This map is injective. So this is there was a theorem, and moreover, its image. You can read its image. Was determined recently by Vadilata, and its image is a complement of two irreducible divisors. Which are explicitly described. Actually, Verziner, in her proof, used the fact that the image of this period map does not meet one of these divisors. But proving that the image is exactly this complement is quite complicated. And of course, the last problem, which is it's not a fact. I mean, it depends how you state it, but it's the problem of rationality. So I think this was discussed in previous talks, so I won't talk about it again. So the upshot here is that some examples of rational cubic fourfolds are known, but it seems to be still not unknown whether there are irrational examples. So this list of results here will be our roadmap for studying other Fano varieties. And to which I want to now explain what these Fano varieties are. They were actually alluded to by Sasha himself. Fano varieties of degree 10 and count number 1. So there is a classification result by Mukai. So it's a bit long to state, but so Sasha already explained actually what this classification is more or less. So assume that X is a smooth prime. So prime means that the Picard number is equal to 1. Smooth prime Fano variety. So prime means pick of X generated by an ample divisor. A smooth prime Fano variety of dimension n. Index n minus 2. So this means that kx is, or minus kx is n minus 2h. It's the divisibility of the canonical bundle. And degree 10. So the degree means here is the top self-intersection of H. Okay, so then so this is Mukai's theorem is that any X like this is one of the following. So this seems like a big collection of varieties, but actually the dimension is limited. So the maximal dimension is 6. So the first case is what we will call the non-hyperelliptic case. So this happens, this happens in dimension 3. So it's either n is between 3 and 5, and x is the intersection of the Grassmannian of two of vector spaces of dimension 2 in a 5-dimensional vector space. So this is our running notation for complex vector space of dimension whatever the index is. And so you take an intersection with a quadrate, and then with a linear space which has the dimension so that x has dimension n. So this is actually 5 minus n hyperplanes. Okay, so it's a complete intersection. Everything here takes place in the structure embedding of the Grassmannian. Okay, so in particular, when n is equal to 5, this is just there are no hyperplanes here, and this is what the Italian classical geometers call the quadratic line complex. So this is sort of a general case, at least when n is not equal to 6, and there's the hyperelliptic case, where basically what you have here is that x is a double cover of, okay, so let me get the numbers right. So it's a linear section here of the Grassmannian. So that, I guess, and a branched along the intersection of the base here through the quadrant. Okay, so in some sense, either you have this case here, or you have a double cover of the linear section of the Grassmannian branch over something which is or the first type, the dimension 1 nest. Okay. So it's a bit complicated. So as you see, there are several dimensions possible, but I will concentrate here on the case of dimension 4 so that we can ask the same questions, questions that are parallel to the one that I listed here for threefolds. But there are also many interesting problems in other dimensions. So what are the results here? So this is in a partial collaboration with Olivier Debarre and Sacha Kuznetsov. So first of all, so let me just, as I said, restrict myself to the 4-dimensional case. So first of all, there exists a modernized space which I will denote by X4 for these smooth Mukai, I'll call them Mukai varieties. Smooth Mukai fourfolds. So this is not as easy as it seems because somehow it doesn't seem possible to express directly. I mean, it is possible to express X4 as a quotient, but either it's a quotient by a non-reductive group or it's a quotient by a reductive group, and then it's we don't know how to prove that smooth fourfolds correspond to semi-stable points. Okay. So we do it in some other way, which will be clear during the rest of the talk. So there is a similar construction of a hyperkähler fourfold associated with X. So one can associate hyperkähler fourfold. So the notation is a bit strange, but so forget about the notation. This will be there's a reason for it, and the X is the origin of X, and I'll explain the rest. So this is a double EPW sextic. I think they were mentioned several times during the week. What can associate with any X. And we have a corresponding same kind of thing. So here, this is a little bit different. I'll write vanishing. I'll explain what it is. We have an isomorphism of polarized Hodge structures. H2. So same thing. So what about the Torelli problem? It turns out that the period map so which goes from X4, our modernized space, to some period domain is dominant. But it's not injective, actually it's fibers. So the fiber and the fiber through a point corresponding to a fourfold X. Okay, so I guess I hope the notation is clear. I take any point in here. It's an isomorphism class of a Mukai fourfold, and the fiber is isomorphic to actually this. So now there's no tilde on it. It's not a double EPW. It's just a simple EPW sextet. So minus maybe a finite set. And when I say maybe, I mean that in general this finite set is empty, but for some special fibers, you need to subtract a finite set, but this is not important to know. Okay, so if you forget about this, a general fiber, generally there is no isomorphism here, no natural isomorphism. So a general fiber of this map is a copy of this EPW60. Okay, what else? Rationality problem. So this is an interesting question, but it's very related to this one, and since we don't know how to answer this first question, we don't know how to answer this other one. I can still say that there are rational examples. This is a very old construction, and again, we expect that a general Mukai fourfold is irrational. Actually, more precisely, we know that some of these Mukai fourfold are birationally equivalent to some cubic fourfolds, which we expect not to be all rational. That's clear? So if you can answer that in a, so I'm not saying that the general fourfold here is birationally isomorphic to this one, but there are examples of Mukai fourfold here which are birationally isomorphic to cubic fourfold which contains smooth cubic scores, and these ones are expected in general to be irrational. So there's a link between these two questions. What I can say here, I'll try to explain that at the end of the talk, is that all fourfold in the same fiber are birationally isomorphic. Okay? So this is an important point because it says that rationality only depends on the period point. Okay, so rationality only depends on period. And I should say also that there are not many rational examples known, but it's just because people have been looking for them. And I assume that a lot of construction, I mean, you can copy a lot of construction that were made by Brendan Hassan, for example, and to produce much more, many more rational examples. For this, the one family we know consists of rational fourfolds. The associated EPW60 or double EPW60 is actually birationally isomorphic to the Hilbert scheme of I mean, here 2 over K3. So the situation is very much like in the case of a cubic fourfold. Okay, so this is the list of results that we have, and
so there are 2 cases in this classification. Is 2 specification of 1? Or
okay, so when n is not 6, 2 is a specialization of 1. It's like a hyperelliptic curve. They fit, yeah, here that includes the hyperelliptic ones. So for example, when n is equal to 6, the first case does not happen, but Mukai sixfold is the same as at least if you forget about the involution, is the same as a non-hyperelliptic fivefold. Okay, so yes, I can erase this. So let me try to explain the analog of this here. It's a bit. There are actually 2 ways to introduce this associated EPW60. There's one that's simpler.
Sorry, what's the EPW?
Nobody wants to explain, right? Okay, I can tell you, yeah, Heisenberg, Popescu, and Walter. Okay, but that won't help you very much.
Just.
Okay, you just wanted to know the name. Okay, the initial, but the construction is a bit complicated, so nobody wants to explain what they are in the talk. And I won't do it. So, to explain the construction, I'll actually start with the 5-dimensional case, because we can do a lot of this. I mean, some of these we can do in any dimension. I mean, any between 3 and 5. Okay. So associated. So I'll take the shorter way to construct this EPW66. So I'll do it in a 5-dimensional case. Okay? Because in this case, a non-hyperelliptic 5-dimensional case, X is just the intersection of it's a quadratic line complex. Okay. So I want to look at the vector space of quadrics containing X. So since this is a complete intersection of a Grassmannian and a quadric, it's not difficult to see that this vector space, which I'll write as Ix of 2, is the direct sum of the space of quadrics containing the Grassmannian, which I abbreviate as G, plus this quadric. So this is the quadric. And quadrics containing G2V5, they are what are called Pucker quadrics, and they're isomorphic to V5. More precisely, anytime you have a vector V in V5, you associate the quadric PV, which takes omega to omega V. So this is a quadric on this vector space here. Okay, anyway, so you see that the space of quadrics containing X is a 6-dimensional vector space, and I want to look at the discriminant hypersurface, that is the set of singular quadrics containing X. So since we are in a 10-dimensional vector space, it will be a hypersurface of degree 10. You're just writing the vanishing of a 10 by 10 determinant. So discriminant. So let me write it in vector space, in P5. So it's a degree 10 hypersurface, as I said. And so it's pretty easy to see that Pucker quadrics have rank 6, that's co-rank 4. So they will count with a multiplicity 4, and they form a hyperplane interior. So it's 4 times this hyperplane. So the 4, as I said, is because Pucker quadrics have co-rank 4. And the there's a word for the rest.
Why is it degree 10?
Well, because
so it's a B5, so there are 6.
No, it's quadrics in lambda 2V5.
Okay, fine.
The residual part, I was looking for this word, is a sextic. So you see, this sextic is EPW sextic. So I don't want to explain what there's a purely multilinear algebra construction of these sextic. It's not really complicated, but it's not very. I mean, it is helpful, of course, but not for what I'm going to talk about today. So I want to do it. And so these were defined by these 3 people, which I named earlier, but studied mostly since then by Kieran O'Grady. He's the world specialist in this 60, hundreds of pages. Okay, so what do we need to know about that? Well, Pucker quadrics, EPW sextic, sorry, can be pretty degenerate, but it turns out that the smoothness, which I haven't used yet actually, the smoothness of X implies that this is not to degenerate. So first of all, so facts, and this is what makes the whole story work actually. Yx is integral, irreducible and reduced. So it's not going to be smooth because this is a degeneracy locus, so it tends to have singularities corresponding to places where the rank of the quadratic drops by more than 1. And but it turns out that so its singular locus is non-empty. But it has the expected dimension. It's a surface. This is what we expect. Co-rank 2. So we expect co-dimension 3 integral surface with finitely many singular points. Actually, if I want to be precise here, these loci are actually really the expected singularities, meaning that these correspond to the smooth points of Yx correspond to quadratics of co-rank 1. These, the smooth points of this correspond to quadratics of co-rank 2. And there are finitely many quadratics of co-rank 3 that correspond to these finitely many singular points, and they don't happen on a general X. Okay, so on a general X, you can replace this by this surface is smooth. It's smooth. These points correspond to the same points that were here. Okay, so this is one thing here. I think this is not actually the right sextic you want to consider. You want to look at the projective dual of it. Okay, so when you have a hypersurface in a projective space, you can look at its projective dual. And what's interesting about this story is that this dual turns out to be, again, an EPW sextic. So, which is called the dual EPW sextic. And it has a construction, a natural construction. So, projective. It's a general fact. Okay, if at least if the sextic is not too degenerate. For example, we take a quadratic, threefold quadratic considered of this 3. This is also an EPW sextic, and we don't want to think about duals. But in this case, which is almost general case, the projective dual is actually, so this is the check, just the list, but this is where it comes from. Projective dual sits in the dual projective space. And it is also an EPW sextic, actually with the same property. So not too degenerate. So why am I looking at this dual EPW sextics? Well, there are several reasons, but one of them is that there is actually a distinguished point in that dual projective space. Correspond to this, the hyperplane of Tucker quadratics. So we have what we'll call the Tucker point. H(x). And one can show that it's actually in the complement of this. Okay, so what we've done until now is start from a smooth, non-hyperelliptic Nikai 5-fold and associate to it this dual EPW sextic plus a point not on it. And so the first result is that this is a
Sorry, but what is the point?
Okay, so the Plucker point corresponds to this hyperplane. Okay, this is a hyperplane in here, so it corresponds to a point in the dual vector space. Corresponding to Plucker products, this is what we call it, product. So the theorem is that the non-hyperelliptic fivefold X is determined up to isomorphism by the pair consisting of yx or yx dual, it doesn't matter, and this Plucker point. Okay, let's put the dual. Okay, so more precisely, this is not very, this is not exactly what I want to say. I want to say that there's a one-to-one correspondence between isomorphism classes of non-hyperelliptic nuclei fivefolds and sets of pairs consisting of a EPW6-stick or dual EPW6-stick and a point not on it. So you can state this in a fancier fashion, yes, in terms of modernized spaces. So it turns out that it's not difficult to construct with GIT methods modernized space for these guys here. It's an affine variety, just as we constructed the, well, I mentioned it, the modernized space for cubic fourfolds. You can construct something which I'll call X5 non-hyperelliptic. Okay. Okay, so this is an affine variety. GIT, constructed by GIT. And so, in some sense, there's a morphism here to the nice space of EPW6-stick. This was also constructed by Kieran already, by GIT also. So here I have to be a little bit careful because, let's put it this way. So there's a GIT compactification. There's a morphism here. The image, so it sends an X here to HX. Sorry, YX. It would be more natural to take the dual here, but I'll do it this way. So the image is a complement of an irreducible divisor. Which already calls sigma. So the image is affine, it's a complement of an ample divisor. And how are we going to, so the fiber of the point in here is isomorphic to P5 to the complement of the dual. Okay? Is this clear? I'm just saying that this is this theorem stated in a different way. I mean, the fact that X is characterized by this pair here, and that you get all possible pairs with satisfying this requirement. So the dimensions here, the dimension is 20, and the dimension is 25. So with this setup here, the set of points which correspond to a EPW6 for which the singular locus of its singular locus is non-empty, correspond to another irreducible divisor in this space. Okay, so this is the 5-dimensional case. It turns out that you can do exactly the same construction in other dimensions. So in other dimensions, meaning 3 and 4, and 5 is so you do exactly the same thing. You look at the space of quadratics containing X, and so there's the there's the hyperplane here of Hooker quadratics plus and same thing, you look at the discriminant locus. And this discriminant is equal to, okay, so 4, the multiplicity here just goes, the Hooker hyperplane here, plus, and this is again an EPW60. So same thing, and there's also a Hooker point corresponding to the dual space, corresponding to this hyperplane here. And so the interesting phenomenon here is that depending on the dimension, the Hooker point will be, so in dimension 5, it's not on the dual EPW60. In dimension 4, it will be a smooth point in the dual EPW60, and in dimension 3, it will be a singular point. So in other words, I can rephrase this a little bit like this. So we obtain moduli spaces, and this is how we construct them. So N is the dimension 3, 4, or 5, non-hyperelliptic, mapped to this. So now that I've defined this is really the image of this morphism here. So this is subjective, and the fibers, depending on the dimension, are as follows. So the fiber of the point, which is the isomorphism class of EPW60 in here, is equal to, as we saw here, P5 minus the dual EPW60. That's when N is equal to 5. Like this. And this is this finite set, which is often not here. So somehow these various moduli spaces fit together to form a P5 bundle over this space. And so it's sort of strange because they correspond to varieties which have varying dimensions, 3, 4, and 5. The way to think about it is, for example, if you put together x5 and x4, So you get something which is has fibers P5 minus this singular surface here. And it corresponds to all nuclei 5-fold. Here are the non-hyperelliptic, and here will be the hyperelliptic ones. So it's a sort of a interesting picture.
So,
Yes?
so you can tend to the in one of the modular spaces.
Yes?
Tend to the boundary and
Boundary in
okay,
the fiber?
Yes.
Okay.
So you will get object of another.
Yes?
Could it be described generically without this?
Yes, yes. It corresponds to a hyperelliptic case. So here's the general fiber. So it's a P5. And here you have the dual hyperelliptic EPW60. Okay? So a point in here corresponds to 5-fold. Okay. When you move in here, you land into something which has dimension 4. But then the flat degeneration of this X5 corresponds to the double cover branch over this 4-fold. Okay. So this is how they fit together. So I guess you could construct maybe a flat family. I don't know if maybe such I can do it. A flat family corresponding to 3 cases, but with all fibers 5. Okay, so are there any other questions? So now I can talk about the period map. So periods of nuclei 4-folds. You can do similar analysis in other dimensions, but the structure of the Hodge structure depends on the priority of n. In dimension 3 and 5, you have a Hodge structure in the middle degree, which is gives you an intermediate Jacobian. For 4-folds, it's a Hodge structure of K3 type. So actually, the Hodge numbers in dimension 5 so they're interesting only in for H4, and it's 0, 1, 22, 1, 0. So this is what I mean by K3 type. So this is the full cohomology. So for example, in the non-hyperelliptic case, your X, your 4-fold is a sub-variety of the Grassmannian. And you really, I mean, the H4 of G is really something that doesn't move. You don't want to consider it. So you want to look at the orthogonal of H4 of G in the H4 of X. Okay, so this is what I called earlier H4 of X vanishing. I used to call it primitive, and then people complained. So this is the orthogonal for the intersection form of the. This has rank 2. Okay, this is why it's a bit different than the. Okay, so here I restrict myself to the vanishing cohomology, so we get a something like that, and so you do the usual construction of the period map. So you can identify the corresponding lattice here. It's not too difficult. So we get in any case we get a period map. From X4 to D. So this D is obtained as a quotient by some arithmetic group of some. I never know which one people call the period domains. I don't know if it's upstairs or downstairs. So this is this Oltian die here. So lambda, of course, is the corresponding lattice, which I mentioned, the vanishing lattice, which is fixed. And so this is a subgroup of index 2 in the orthogonal group of lambda. And okay, so in particular, there is any element which is in O lambda and not in this one will induce an evolution here, which I'll call RD. It's a covering evolution to the quotient here. Okay. So this is one thing, and so now.
How is it defined, this evolution?
It's the covering evolution. Yeah, this is a full group. This is what people call the stable orthogonal group. Okay, so now I can skip a little bit what I wrote here because it was already mentioned in previous lectures. There is also, yes?
So this was radical construction, this was very projective duality.
Yes.
From AKW-16 to AKW-16. Can you be seen?
Of course, yeah, it's the same. Yeah, yeah. Because it turns out that, so there's a period map also. So we get period maps. So the first one here is for our fourfold, but there's also a period map which was studied by O'Grady. Okay, so if I want to be precise, I have to. So this is the hypersurface in the moduli space, which I already took off. And this one corresponds to. I'm going too fast here. I'm going too fast. Yeah, I forgot to mention something. What is this period map here? So something that I should have done earlier. It's I haven't done it yet. No. It's this double equilateral. Whenever you have an equilateral, you can already construct a double cover. Which is ramified, at least in non-degenerate cases, over the singular locus of this sextic. So remember, at least in general, this is a fourfold which is singular along the surface, and the surface is smooth. Okay? This double cover is ramified in dimension 2, and it turns out that this fourfold here is smooth. At least when the surface is smooth, and it's a hyperkähler fourfold. So that's the what makes this whole thing interesting. Is that out of this strange singular object, you can produce the hyperkähler, smooth hyperkähler fourfold. And this is canonical. With polarization, I should say, polarized. And this double equilateral form a complete family of hyperkähler fourfolds. And this period map I wanted to talk about is the period map for these smooth objects. So taking off this second divisor here, which I hadn't mentioned before, corresponds to restricting yourself to a smooth surface angle. It's not really important. So we have a period map, and it's actually the same period domain, which is what we should expect, since I mentioned earlier that the Hall structure here is actually isomorphic to the Hall structure of the W60. So what's important here is that we know by the Iskovskikh theorem that this is an open embedding. And actually, this period map was extended by O'Grady to this slightly singular case. So, and proved that the extended map is also an open embedding. So, I can erase this. But these are technical details. You don't need to pay attention to that. Okay. So remember that we have this map here. It's some kind of locally treated, not locally treated, but it's a fast map. And so, of course, the question is whether this diagram commutes here. By the way, there's this is referring to Claire's question here. There's the projective duality, which induces an evolution of on this space. This divisor turns out to be stable by this evolution, so it's okay. And there's the this evolution here, and already proved that the projective duality corresponds in terms of period to this evolution. Okay, so so the theorem, I guess, is that this diagram commutes. Actually, this is why I think we should change the definition. But if you want really to have commutation, you need the evolution here. So one way to fix that would be to define this P4 map by sending x not to yx, but it's to the dual. Everything would be more natural. But then the fibers would be better. So this commutation here corresponds to an isomorphism between. So commutativity corresponds means maybe quotes here. Anyway, what we are really going to prove is that there's this isomorphism. Here's the primitive part. Okay, so if you remember how I defined this space here, it seems totally impossible to prove anything like this, because we started with a space of singular quadrates, and then we constructed a sextic, we took its dual, and then there's a double cover construction. The way we're going to prove this is actually similar to, in case of the cubic fourfold, the situation was there was a direct relation between the cubic fourfold and the space of lines in that way. And this isomorphism was actually induced by the Abel-Jacobi map between these two spaces. Okay? Every time you have the space that parametrizes the cycles in here, you have a Abel-Jacobi map between chronology. And so we need to relate this space here to something geometric on X, and these are going to be conics on X. I can do the construction in general. Maybe I'm not sure I will use it. So the construction is as follows. So let me call f of x the Hilbert scheme of conics containing x. Okay, maybe reducible, maybe non-reduced. There is a rational map from f of x, so the space of conics, to the dual space of conics containing x. Simply, you take a conic here, and assuming that the plane spanned by the conic is not contained in x, you can associate to C the hyperplane. So this the hyperplane in Ix of 2 of quadrics containing this plane spanned by C. I should say, maybe I'm not sure I ever mentioned it, but X is an intersection of quadrics. So whenever this plane is not contained in X, this is indeed a hyperplane, and so you get a rational map like this, which is defined exactly on the set of conics which satisfy this property. So this is a very interesting map in all dimensions, and this is maybe how one should start while doing these constructions. So let me actually stick to the case when n is equal to 4, although, as I said, this is interesting in all dimensions. When n is equal to 4, so theorem, so n is equal to 4. So let's say that X is a smooth, non-hyperelliptic nuclei 4-4. So the expected dimension of f of x is 5. So let me put it this way: f of x always has pure dimension. Has pure dimension 5. Its irreducible components are, so there's one which I'll call the main component. And then the other components correspond to various planes contained in S. So this, so P1, PR are the planes in X. So this is just a space of conics contained in a plane, so it's 5-dimensional. It's a 5-dimensional projective space. And okay, and so the map right here is not defined, of course, on this plane, but it is defined on this main component, and its factors as follows. So phi restricted to phi main. Okay, so like this. So the image is actually the dual UPW system. So this is really what makes things work. And what's nice also is that it factors through this double cover. So this is the canonical double cover. And this is more or less the P1 fibration, but only generic.
To one fibration, there is a degree 1 line bundle, or
No, it's a P1. Let's say that the fibers are rational curves, general fibers. It's more like a conic fiber. So why didn't I start by just looking at this picture, which is more geometric and more useful for our purposes? Well, it's because that we don't know anything about this space here. I mean, so it was first studied in a paper by Ilief and Manifolds and Aldebanes. And they span many pages proving that this space is smooth. And then they construct this, they prove that it is smooth, and they construct this map here, and so on. And they can only do it when X is general. There's a lot of genericity argument in this paper. Whereas in this fashion here, because proving that the EPW6, the original one, is rather nice, meaning not too singular, almost general, implies that this one also is general. And then we can go back and actually prove that in most cases, but really explicit cases, this space is smooth. I mean, this picture is actually clearer because we already know that this is nice. A priori, it could be anything. I mean, this is a consequence. The 2 is actually a consequence of this. Okay, so what was I saying? Okay, so next remark is that when X, the space of 4 folds which contain a plane is really well controlled, corresponds to a certain divisor in the period space, for example. So in particular, in general, there are no planes here. And in general, so there's f of x is irreducible, and it is actually a smooth. Okay, so once you have this, you're in a pretty good shape to at least produce a morphism like this. In the same fashion as a Abel-Jacobi morphism. But at least up to now, we don't know enough about this. I mean, if you do some blow-ups in here, you can actually reduce to the case where this is a harnessed P1 vibration. But I don't know, maybe you can do the computation directly like this. But at the moment, the only way I know how to prove this is sort of so first of all, it is known that in general, the corresponding cube Hodge structures here are simple. So by a simplicity argument, I'm trying to prove that this map here is an isomorphism. By simplicity arguments, you can show that it is injected. And so to prove that it is an isomorphism, I actually reduce to the case of qubits. When X contains a plane, there are 2 kinds of plane in the Grassmannian, and it contains one kind of plane. By projecting from this plane, you show that it's a very old result, which is already in Fano's papers, that it is birationally isomorphic to a cubic threefold.
You mean 4-4?
And then you sort of play around, and you show that this double EPW6 is actually not isomorphic to f of w, but it's a Mukai flock of f of w. And then you use the Gaussian-Delahaye result to deduce this. So it's not a very satisfactory argument. And, I guess a direct calculation would be more pleasant, but still maybe also messy. Anyway, so this is how we prove this statement here.
Which cubic fourfolds do you get?
Okay, so we get cubic fourfolds which contain a, by projecting from a plane, I wrote it down because I always forget, containing a cubic swarm. So they're special, but they form a divisor. They were actually studied in a very nice article I liked very much by Hassett and Chico, and they studied the geometry of this. It's very nice. Okay, so I wanted to explain the last topic of the talk was how to relate rationality problems. Let's go this way. So just for fun, let me write down what is known in all dimensions. When n is equal to 6, I don't think that the Mukai sixfold are probably rational, but I don't think anybody ever bothered to think about it. When n is equal to 5, so I don't know if Sasha would. They're all rational. Yes, yes. Okay. I'm asking you to write it down, but he's resisting it. But they're all rational. Smooth ones. Maybe non-hyperelliptic. The construction actually already appears in an article by Rod in the 40s. But of course, it's now good for general. I mean, in these days, I think general and theory was sort of the border between the two was not fixed. Okay, so when so this is not well, you can say that. The answer is no. So when n is equal to 4 and 3, they're unirational. There's a rational 2-to-1 cover. When n is equal to 3, it is known that the general one, general x3, is not rational. You can find that in Arnold's first article, thesis, I think. First or second. First or second, yeah, one of the two. It's by degeneration technique. You show that there's basically you show that the intermediate Jacobian is not the Jacobian of the curve. So it's kind of with this technique. This is all that's known. Okay. When n is equal to 4, as I said, there are rational examples. Not these ones, but examples of fourfolds which contain some special surface. There are, which I don't remember. Quintic del pezzo, right? So if X contains a quintic del pezzo, then it's rational. This is by a projection argument, and this fact here can actually be read on the period point of X. This is the what Hassett called special varieties in the case of cubic fourfolds. You can do the same here. It says that the essentially the H4 contains a special class. And so you can something you can see on the period. So what I want to explain here is that rationality actually only depends on the. This is a general fact that rationality only depends on the period point, or if you want, only depends on the associated level 6 state.
So when the X contain plane, it is not expressed to be rational.
A cubic, which is expected not to be rational. There are two kinds of planes, and I think there's one. Okay, so I don't think so. No. Let's see. I don't think they do. It's like in here, actually. You prove this by showing that when they acquire a node, the intermediate Jacobian is not the degeneration of Jacobian of curves. Okay, so if you put it between quotes, one times material. So how do we do this? So this is we actually construct an explicit birational transformation between two fourfolds which are the same period. And so the idea is what people call conic transformations. So these conic transformations were used very much in the classification of Fano threefolds. And so for threefolds, in general, it goes like this. So assume you have a Fano variety and contains that it contains a conic. So this is a subset, this is a C. And so you project from the conic, assume that C is smooth, so there's factors, and that X does not contain X is an intersection of quadrics again. So it factors through, it defines a morphism on the blow-up of C. And so the Picard number here is 1. So the Picard number here is 2, and the two contractions corresponding to the two extremal rays are this blow-down morphism and this one, if it's not as morphism on its image. In a lot of cases, this is a small contraction, and it's kx trivial. You can plot, and you get some other ID. And so again, it has two. The Picard number here is 2. And the two, so one contraction is this one, and the other one has to be kx negative, so it actually exists by Zory's theorem. So you get a Zory contraction here. So, and the conic transformation is the result. So this is birational. This could be anything. But in any case, it defines a rational map like this. This could be dimension here could be smaller than this one. So this kind of transformation is very much used in classification of Fano threefolds. You can look it up in the encyclopedia. The book with Debarre and Iskovskikh. And we can actually we can try to do the same in our case. And so maybe I should say something specific to dimension 3. And that flops preserve smoothness. So, for example, when X is a Mukai threefold, and C is a smooth conic containing X, so the miracle here is that the X prime you get, which usually is very different from this one, and this is useful because you produce unexpected maps between different Fano threefolds. It turns out that when X is a Mukai threefold, X prime is also a Mukai threefold. It just happens like this. But it's also smooth. So we can try to do the same in dimension 4. There are some technical problems. So one can show, using this, one can show that the X prime is actually also the Mukai fourfold, but maybe singular up here. But it might have a finite number of single points. The problem is that when you flop here, there's no guarantee that the result will be smooth. In any event, you can still do that. And so the facts are the following. The EPW66 let's say, okay, I'll be entirely correct here. When X is general, actually X prime is also general in the mosaic space. So in this case, I can consider the EPW66 actually. So the facts are that they are actually isomorphic. And but of course, X prime could be just isomorphic to that, but this is not the case. So yeah, this isomorphism, let me call it the Cooper point. So let me put it as isomorphism, which is the dual. So this is one thing, and the Cooper point. So H X prime. The Cooper point of this one is actually the image of something which I call phi of C. So I don't know if you probably don't remember what phi was, but it was this map between the space of conics to rational map and define actually of C. Okay, so to put it in a few words, you've constructed another Mukai fourfold with the same EPW60, but whose Cooper point is different. Because the new Cooper point is the image of this conic here, which is more or less any point. Is this clear? No, that was in dimension 5. In dimension 4, it's actually in the 6. So in some sense, since you can vary C here, I mean, there are some problems because in this construction we assume that C was smooth. But in any event, this is why I put quotes in here because I'm not entirely sure that this is true, but it should be. In any event, by taking C, even if you restrict yourself to C smooth, you cover at least an open set here of varieties which are all birationally isomorphic to the original X. So in other words, situation is like this. So this is the map to EPW, or you can think of it as the period map. So your original X was here, corresponding to a point HX. And by conic transformation, you can move almost anywhere to a new one. So this was a point H, and this is a point C. And so all the points here in this big open set correspond to birationally isomorphic fourfolds. So maybe what if you want to prove that any 2 points in here are birationally isomorphic, the way to do it probably is to do 2 conic transformations. Then you have 2 open sets, and you can hope that they cover the whole thing. Well, I think we have time to stop here. Just one more word. I guess this elementary transformation more generally not being used in high dimensions because of this problem of similarity of the image. But they might prove useful to prove, as they were in dimension 3, to prove to discover unexpected maps between various fourfolds or even fivefolds, and even in higher dimensions. Okay, so I'll stop. Thank you. Questions? Comments?
Vous avez une certaine similarité avec le fourfolds.
Yes.
So, do the varieties have a very big birational isomorphism group, like the cubic
well, I don't know. Well, some of them are birationally isomorphic to cubic fourfolds. In general, I don't know. I don't know. More questions?
We will have a next talk in 15 minutes.